You're probably wondering, should I get up this early to come and listen to some dingling, fill my ear about antennas of all things?
Yeah.
Well, all right. Give me a little boost. Well, just a little bit of background. I won't bore you with much of that stuff. I'm Gary, K7 EMF, and this is Molly, the manufacturing manager of TrueLadderLine and antennas. And you wonder, how in the world did I ever get into ladder line? So I'm going to make this quick, but we're going to keep it light so you don't have to think a lot. I got my ticket in '62, and back then, the majority of the hams were using ladder line. And being 16 years old, I'm looking at ladder line and thinking, how am I going to implement this stuff? And coax was coming on the surplus market. And I'm thinking, boy, this coax is mighty easy and it's probably all the same. So I made the big mistake of starting up all my antenna projects, feeding them with coax. That went on for a lot of years. I tried most every antenna imaginable. And I got pretty fair results, but I noticed that there were a couple of 3 hams on the air on 75 meters that always, when they came on, they pretty well put my S meter to the pin. And when the band was closing out, they were the last ones there. And so I worked really hard for many years to figure out which antenna they were using. And it turns out it wasn't the antenna at all. So fast forward many years, about 20 years ago, I finally gravitated to a track dipole. Had up about 70 feet pine trees, fed with RG8, and it worked quite well. And then I got a wild hair. I think I need a new project, so I thought, well, I'll just build up some ladder line and replace that RG8 with ladder line. Everything else stayed the same. Fired that thing up on 40 meters using a Icom 751A, feeding into a T-network antenna tuner, feeding the balanced line. Tuned up on 40 meters and everything tuned up great for about a minute. And then reflective power went against the pin. Shut it off, went outside, and my whole antenna is laying on the ground. And I look over and here's one of my traps smoldering in the grass. And I said, Gary, you are an idiot. And that was the beginning of a whole new deal for me. So later on I ended up purchasing some TrueLadderLine from Brian, who some of you probably have dealt with. Very nice gentleman. And I built up a 215-foot long dipole, center fed, simple, fed with TrueLadderLine, and we're operated on 160, 80, and 40. And there's a reason for that length of antenna, but we'll get into that later. So anyway, then we decided to move from northeastern Washington to Arizona, so I sold all my tower stuff and antennas to a fellow by the name of Tom, KD7 VAR in that area. And as he was loading the stuff up, I coiled up my antenna and ladder line. I handed it to him. I said, Tom, I'm going to make you a present. Take this. And I explained why he needed to put this up in the air. And he looked at me like, Gary, I really have a hard time believing what you're saying. I don't think this is for real. I wasn't selling it to him, I was giving it to him. So he took it, and I figured, well, that's probably the end of that. So then, about 6 months later, we ended up acquiring TrueLadderLine and antennas. And part of the deal was that Molly would be the manufacturing manager because I'd already retired twice in the broadcast engineering industry, and I didn't want another job. I wanted to play a little bit on the air. Well, that didn't quite work out either. So anyway, Molly took over the manufacturing and started building ladder line. and we added the 450 TrueLadderLine to our list here recently, our product list. So anyway, about 6 months into that, I get a call from Tom, 87 VAR. And I had no idea what he was using for the HF, low band HF antenna before this. By the way, I forgot to mention, we're talking about today about a multi-band antenna, 160 through 10 meters, no traps, no coils, none of that stuff. And the frosting on the cake is, I have seen 98% efficiency. So we'll get back to that. So Tom calls me up and he says, Gary, he says, I put up your antenna you gave me. And he said, I got to tell you, I am absolutely blown away. And I said, well, what happened, Tom? He said, well, I have 2 Double Bazooka antennas up. I've been using them for years. And he said, I've had trouble on 80 meter, 75 meters AM because I couldn't hear the guys very well. He said, I put your antenna up, and all of a sudden it's a whole new world. So I said, Tom, would you please send me a video? And he did. Would you like to see it? Please. Okay. By the way, this is on our website.
Okay, Gary, that is the Double Bazooka.
Evidently, so I put it back in the case.
That is your antenna.
I've talked to Keith about it since then, and I'm going to take it over to him on
the non-resonant fed with ladder line.
Things to do in
and that's
town.
Brent down there. Okay, back to the Double Bazooka.
Buddy is have to undergo another.
That's the Double Bazooka. This is why I was having such a hard time hearing everybody on AM.
Together on Monday, and it'll probably be our last chance to do that for a while.
Back to your antenna.
After his next round with
that is amazing. I just still am shocked.
Sounds like he's going to have some kind of a implanted.
I'm going to let this video play for a minute.
Radioactive device that they
Double Bazooka right there.
Put a new one in every week.
And when Brent's done talking,
must be a material that dissolves away over time, and he's got.
Look at that, he's almost faded out.
Strict regimen that
and
he's
you
going to have
click it back to
as
the
far as going to the bathrooms, got to stay
non-resident antenna fed with ladder line and the tuner at the tower.
A whole long rigmarole of stuff he's going to have to endure. I sure do not envy him. Anyway. So
what a world of difference.
That thing over there to Keith Monday afternoon and leave it with him for a while.
This might be a long one with Brent talking.
On with it. On the Collins S line, I've got that working pretty good.
This is the Bazooka antenna.
The power supply that Lee and Keith found down at Rickreall. It's a nice one in a cabinet. It has a start relay mod.
Back to your antenna. Non-resident antenna fed with ladder line.
Protection device on the AC.
Both of them up about the same height.
Then all
and oriented just about the same direction.
It should be a good, rugged, dependable power supply for.
Matter of fact, the Double Bazooka is closer to the shack.
The initial one that came from OSK will become the spare. So that's what's going on.
There's the Double Bazooka
operating desk
right there.
I'll turn it back to you. See if you have questions
and then
or comments.
The non-resident antenna.
Yeah, and we got a BNZ in. Hello, Steve. And once again,
that's the Double Bazooka.
AC7DA and Group W0.
Non-resident dipole.
Okay,
fed with ladder line.
Good update on the Collins stuff.
Amazing. Just amazing.
And sounds like you got.
Okay. So, quick question for you. Does everybody remember their first contact?
Yeah.
Y'all do? Anybody not? Oh, we got a couple. Okay. Well, for me, that first contact was pretty much a miracle. And it's something I think about quite often. And I can remember the whole issue was, for me, the antenna. I was using a homebrew transmitter, a old Hollow Crashers SX43 on CW, of course, for the novice. And I found after putting up several antennas that they usually work a fair amount better when you put them up in the dark with about 2 or 3 feet of snow on the ground. Maybe a little bit of snow falling. I mean, it doesn't get much better. You feet back inside. Your hands are so cold you can't hardly run the radio to see just how this antenna is going to work. And for many years, that's the way it went for me. You know, how is this new antenna going to work? How do you evaluate an antenna? Any of you have that experience? All of you, right? Yeah, okay. Okay, that being said, I hear on the air a lot about, I put up this new wire antenna, the dipole type of antenna, single straight wire, and I think it has some gain. So let's talk a little bit about gain. We'll get in a little bit of the nuts and bolts here now. So gain of an antenna is characterized by a reference antenna. There are 2 reference antennas that we have. One is an isotropic, which is an imaginary antenna. It's impossible to build. And the other one is a dipole. So when someone says, my antenna, I'm told my antenna has a gain of 6 dB or 3 dB. My first thought is, of a joke I used to hear, was about these 2 individuals, one on each side of the river. And one said to the other one, how do you get to the other side? And the second one says, you're on the other side. So, well, that's the way it goes with dB of gain. So to specify it properly, an antenna has gain in terms of an isotropic, which would be dBi, a dipole would, or an antenna would have a specification in terms of dB of dBd. That's dB over a dipole, dB over an isotropic. The dipole in free space shows 2.15 dBi. So why does a dipole show gain over an isotropic? And the answer is the dipole is not an omni pattern, not equal all the way around. On each end there's a null. So that energy is moved from those nulls out around to broadside on it. So you can think of it just moving the pattern around. So that's how a dipole ends up with 2.15 dBi. So what do you suppose the dipole gain would be rated at? If I throw up a wire in the air, a dipole antenna, what would the gain of it be? Any takers? Paul?
0.
That's right. 0 what?
dB? Yeah, dB.
Yes. Thank you. So what's your first thought when you see an advertisement from an antenna manufacturer and they say this antenna has 3 dB of gain? What do you think? Any takers? Not too impressed, right? When I see that, I just keep on going. I just don't even mess with it. So if they rate it, a lot of times they'll rate it dBi to show a bigger number. So 0 dBd is equal to 2.15 dBi. They're both equivalent. So, why are we concerned about gain? Well, with most antennas, we want to know what the gain is, but it's not a free lunch. So gain also dictates that the antenna has directivity. So any antenna with gain has directivity. That is a law of physics. It's just like a flashlight. You have a single light bulb shining, it's all the way, the pattern's all the way around, isn't it? If you put a reflector behind it, now it's got a beam. It's like a Yagi antenna. So we've taken that energy and moved it around, if you will, and focused it in a direction. So that antenna has gain. So on the HF bands, and specifically 160, 80, and probably 40, it would be great to have an antenna with gain, but then we'd also have to rotate it, wouldn't we? If we don't rotate it, then we're losing coverage. We have gain going this way, we're losing it over here, so then we want to rotate it around like we would on, say, 20 meters with the A. Well, it's just not going to get it for most of us. So we're looking for an antenna for 160, 80, and probably 40 for most of us that would have an omnidirectional coverage all the way around 360. We can do that with an inverted V. Inverted V is very close to an omni pattern, not quite, but close. So that being said, how do you rate a wire in inverted V? How do you place merit on that wire? In other words, we can't use gain because what's the gain of the antenna? Roughly 0 dB, isn't it? So how do we rate this antenna between good, bad, and ugly? As an example, an HF mobile on 75 meters. That's ugly, to say the best. Why is that? Well, somebody said efficiency over here. You're right. That's right. Why is an HF mobile whip on 75 meters so inefficient? It's still a good rate here. And the answer is the impedance, the feed point impedance, is extremely low, somewhere less than an ohm. So when you pump 100 watts into it, apply your I squared R law, Ohm's law, and the current is sky high. When you have a lot of current in a fairly small conductor and an inductor, what happens? You got yourself a space heater. And that's exactly why an HF mobile is so quick on 75 meters. So, there's only one way that I know of, and this is something that I got figured out just a few years ago, that this whole issue is not just the antenna, this wire antenna, but it's also the feed system and the ATU. You have to put it all together. And when you put it all together, now you can see the efficiency of the system. So basically what that's telling you is, I'm giving so many watts to the antenna, where the antenna can do its job. If I'm not getting the watts there, you know the rest of that story. In fact, it reminds me of a customer of ours. He's at the show. He's running his radio remotely, and he has a 1500 watt amplifier on it he's been running. He's using our ATU and TrueLadderLine, and it's a center-fed dipole, and his amplifier died on him here recently, so he's running at 30 watts, no choice in the matter. And he told me, he says, most of the stations don't even know I've lost my amplifier. And that's because of a good antenna, an efficient system, not just the antenna, the system. So so we're going to look at efficiency instead of gain. We're going to put gain on the shelf for this discussion, because gain, first of all, we're not interested in gain as it were on the low bands because we want an omni antenna. Okay, so we apply that physics, law of physics. So, characteristic impedance of a feed line. You want to get some? So, there are two types of loss measurements for a feed line. The one that's published is what we call matched losses. In other words, if you have a 600 ohm line, if you have a 600 ohm load on the end of it, the specified number that you can look up on the internet and find SWR charts. And by the way, transmission line details is where I would recommend going. It's a great program. It has all the feed lines in it, and it's free. Transmission line details. You can look up any feed line you want in there. You don't have to search around for it. load in the number of feet and the frequency, and you've got yourself a loss table. The other neat thing about it is you don't have to interpolate off the table. You just load in the frequency and it tells you what the loss is. So as an example, 600 ohm ladder line from TLD is 0.05 dB per 100 feet. The other loss that all feed lines exhibit is what we call mismatch losses. Mismatch losses would essentially be due to SWR, standing wave ratio. In other words, we have standing waves on the line, we're going to have additional losses. And this is the issue that we're dealing with, we're going to be dealing with, because we're operating a multi-band antenna with one antenna, one feed line, no tuned circuits. We're going to have high SWR. So the rule here is to keep coax out of a high SWR part of the circuit. In other words, coax should only be operated in a one-to-one condition. So what do we use? We need low-loss feed line in the high SWR part of the circuit, and there's only one choice. Well, there's two choices. There's ladder line, or there's big coax or waveguide. Well, we can only afford ladder line, and it's a lot easier to install and hold up in the air. The Navy chose 600 ohms as the best choice for impedance of ladder line, primarily because of the efficiency of it again and low loss. So why do we use coax? There is a good reason for coax. Being in the broadcast industry, building TV stations, I work with a lot of resonant gain, high gain antennas. And we've installed coax up to 8 inches in diameter with feed line to the antenna. And that is also quite low loss because of the conductor size. So why in the ham community do we use coax? And there's only one reason. One reason. Because a resonant antenna provides a 50 ohm non-reactive load to the antenna, to the feed line. So it terminates the feed line at a 50 ohm non-reactive load. And when that happens, that coax is exhibiting the matched characteristics from the chart, basically low loss. So if we, and the definition, by the way, of a resonant antenna would be one that the feed point exhibits no reactance. So it's the crossover point. So another law of physics. When you deviate from a half wavelength antenna, which has a theoretical 50 ohms and no reactance or very low, as you shorten that antenna, the impedance, the feed point impedance, remember there's two components to impedance, resistance and reactance. The resistance component goes down fast. And that's the reason why an HF mobile antenna has such low resistance. Part of the impedance is because it's extremely short compared to a wavelength. At the same time, it goes capacitively reactive. And that reactance goes up as you shorten the antenna. Or if you QSY from resonance, you go up the band, down the band, same thing. So, conversely, if you deviate from a resonant antenna and you go up the band, the antenna feed resistive part of the feed point goes up, higher in resistance, and it also goes inductively reactive, and that goes up as fast. So you can see by sticking 600 ohm line on a dipole, no matter what the length, you're never going to have a low SWR, ever. It's not going to happen because either the resistance is going to be incorrect or it'll be reactive. In either case, you have standing waves. You can't get around it. So that's why for multiple bands, and by the way, as soon as we QSY from the resonant frequency, QSY just a few kilohertz, that antenna now is a non-resonant antenna. So I hear people say, I've got it, I'm tuned to resonance, this thing should work. Well, dummy mode will do the same thing. So this is the reason why we're not worried about resonance. We're not worried about the length of the antenna, except that by changing the length of the antenna, we'll change the feed point impedance. So the design criteria is to find an impedance at the feed point that results in the lowest SWR on the ladder line part of the feed line. So if we can get that down, I'd like to see 10 to 1 or less. And when we're running 10 to 1 or less with ladder line, our efficiency numbers are better than 90%. So it gives you an idea that this feed line is near to a perfect feed line. Not quite, but close. So how do we characterize, and up until a few months ago, well actually a couple of years ago, I found it very difficult to characterize my entire system to know what my system efficiency is. It's just difficult, almost impossible. So finally, a gentleman in California, AE6TY, came up with a program that, by the way, is free. It's called SIMNEC, SIMNEC, and it's also listed in our website, in our store, under private categories, and there's a link there where you can pull it up. I'd be happy to show that to you if you'd like. And with that program, it's an incredible program. It uses NEC, the same engine that EasyNet uses. You load in your antenna parameters, elevation above ground at both ends in the center. We also do loops. And feedline length. And then you can actually, it will tell you instantaneously the feed point impedance, and inside of the program we have each of our circuit elements in there, and they all are shown. We can actually tune the ATU right in the program, and we can see the results on the Smith chart. And when we've acquired a 50 ohm non-reactive impedance to the transmitter, we have a resolution. We can see right in SIMNEC what the inductance is on the tuner, and also the capacitance of the variable capacitor. And the frosting on the cake is that over on the top left, we can also see how many watts are going in the antenna. So now we have ourselves a efficiency percentage number. So for the last couple of years, we've been modeling antennas. By the way, we can also see how much power is being dumped in each element of that system all along the way. The inductors, capacitor, feed lines, all. It's an incredible program. So we've been modeling for customers at no charge, and we'll continue to do that. And I've modeled a lot of antennas for a lot of hams around the country, and we've had some really nice results. And if we see a problem, as an example, I just did a model for a fella, KA9DZR, with a 574 foot loop, and his efficiency came out to 43.7%. That's because he had a bunch of coax out in the high SWR part of the circuit. So there's a way to fix that, and I did fix it and got it up to 97.6%. So without this software, we're just really out there flying in the blind. So before we, and I'd be happy to show you, what time is it, Molly?
9:48.
9:40. All right, we're about halfway. Well, past that. We have 10:15, I think we're done. Okay.